In this video, we'll go over some practice problems on the material covered in week 7 of this course. So we're going to start with section 5.3 here, and in this section, what we're doing is factoring special types of polynomials. And so here's a summary. This is a screenshot directly from the book in section 5.3, but this is a summary of the different or special types of factoring. So when we're factoring polynomials like this, for example, let's look at question 7 here. It'll be helpful to first rewrite this polynomial, if possible, to match one of these forms here. So notice we have p squared minus 16, and 16 we know is a perfect square. This can be rewritten as p squared minus 4 squared, since 4 squared is 16. Well, once we rewrite this polynomial in this way here, notice that we have a difference of squares. So in this case, we have p squared, so p is our x, and then y is our 4. We have p squared minus 4 squared. So that means we can factor that guy exactly like this here. So factoring this polynomial, we're going to get p plus 4 times p minus 4, just following our format for our difference of squares here. So that's how we do this problem there. Now we can factor question 10 here in a similar way, in that we first maybe want to rewrite this. Notice that 36 and 25 are both perfect squares, and we're taking the difference of these two terms. So that kind of gives us a little bit of an indication that we're again dealing with the difference of squares. So rewriting this, we know that 36m squared can be rewritten as 6m squared, and then 25 can be rewritten as 5 squared. So again, we have a difference of squares, and we can use this here to factor this polynomial. So doing so, factoring this after rewriting it, we're just going to get 6m minus 5 times 6m plus 5. Now this next question here, 23, might be a little bit daunting at first, but going back to our summary of our special types of factoring, it seems to almost match this form here, our perfect square trinomial. Our first term is a square, our last term is a square, and our middle term is 2 times the product of those two variables. So going back to this guy here, notice 4 is a perfect square, and then we have square of this variable and the square of our last. And then this can be rewritten as 2 times 2 of the product of these two variables here. So what we can do is rewrite this polynomial in that form. This is the same thing as 2z squared plus 2 times 2zw plus w squared. Now going back to this guy here, it matches exactly this form. So this means we can factor this polynomial just like this here, but in our case, this x here will be our 2z and this y would be w. As we have here, this first term squared is 2z, so we'll have 2z plus our last term here, which is w, and then this whole thing is going to be squared. So that would be our answer here. And then just something to note here, we're just following this exact form with our perfect square trinomials. And in the case we just looked at, we had the sum of all of these three terms. If we had that this middle term was being subtracted out, we would use this to factor it instead. So just something to keep in mind there. So with that being said, we have question 32 here. So this also reminds me of a perfect square trinomial in that our first and last terms are squared, and then we have the middle term is going to be the product of our two variables here. Now in this case, we're subtracting out our middle term, so this kind of gives us an indication that we're looking at this case here. However, before we can actually factor this, we need to rewrite this so it matches the same form as our perfect square trinomial. The first thing that we can do is pull out a common factor. Notice that 80, 40, and 5 all share a common factor of 5, so pulling that out of our polynomial, we'll be left with 16z squared minus 8zw plus w squared on the inside there. Now from here, this polynomial is going to become a little bit easier to factor using the fact that this is a perfect square trinomial when we rewrite it matching that form. So what I mean is, on the inside here, this 16z squared is a perfect square term. So we can rewrite this using the fact that 4z squared is the same thing as 16z squared. Now this middle term here, we could factor this out so it matches this exact second term here in our perfect square trinomial. But notice in the end, but this doesn't really play a part in our final answer here, our final factored form, so I'm just going to leave this middle term as is. Then our last term here is a perfect square. We have w squared. So from here, our 4z and our w become our x and y terms in our factored form. Now, we also know that we're subtracting out this middle term, so our final factored form is going to be the difference of these two guys. So this 5 is still going to hang out on the outside, and then this factored polynomial on the inside will be 4z minus w, and this whole thing is going to be squared. So this would be our final factored form of this polynomial. Now for this next example here, we again want to factor this polynomial, but first notice that 8 and 125 are both perfect cubes. Also, we're taking the difference of these two terms. So this kind of gives us an indication that we're dealing with the case when we have a difference of cubes. So what we're going to do is again just rewrite this polynomial to match that exact form. We can do that by using the fact that 2w cubed is going to be the same thing as 8w cubed, and 5 cubed is the same thing as 125. So just so we don't have to keep scrolling up and down, I've written our form for our difference of cubes here in blue. So as we can see, we've rewritten this polynomial here to be in this exact form where we have a difference of cubes. Now, in this case, our x term is going to be 2w and our y term is going to be 5. So what we're going to do is plug our x and y terms into this fully factored form here. So if x is 2w, then we're going to have 2w, and if y is 5, we're going to subtract off 5 here. Now we're going to multiply this by 2w squared. Since we have x squared here, this whole thing is going to be squared. So we'll have 2w squared minus the product of our x and y. And our x is 2w, and we're going to multiply that by y, and then we're going to add y squared. So from here, we can simplify this a little bit. We have 2w minus 5 on the outside still, and then 2w squared is going to give us 4w squared. Then our second term here is going to give us minus 10w, and then our last term, we're going to add 25 here. So this would be our fully factored form when factoring this polynomial. And so just as a reminder here, this is the form that we're looking at. So that means our x is going to be this 2w since this is the whole thing that's being cubed. And then our y is going to be 5 since this guy is what's being cubed. All right, so for the last question in section 5.3, we have the sum of two terms here. And notice that both of these terms have a cubed on the end. So this kind of gives us an idea that we might be dealing with now the sum of cubes. So what we're going to do is rewrite this polynomial to see if we can get it into this form here. So first of all, we want to notice that both of these terms share a factor of 3. So what we can do is pull that factor out and see what we're left with. We're left with on the inside, 8n cubed is our first term, plus 27p cubed. Now notice we're left with 8 and 27 as the coefficients of these two terms, and those guys are perfect cubes. So the inside of our parentheses here can be rewritten as 2n cubed plus 3p cubed. So now notice the polynomial on the inside of our parentheses here is going to be the sum of two cubed terms. So I have the form for our sum of cubes here. So in order to factor this, we're going to follow this form here. Now in this case, our first cube term, x, is going to be 2n, and then we're adding our second term, which is going to be y, which in this case is 3p. So we're going to plug that into our fully factored form. Now we still have, let's give us some room, we still have this 3 on the outside. Now this 3 is going to multiply our x plus y, so that would be 2n plus 3p, since those are our x and y's in this case. And then we're going to multiply this by the square of our x term, so 2n squared. And this whole thing is going to be squared, so it looks like this here. Then we're going to subtract off x times y, so this would be 2n times 3p, and then we're adding the square of our y term, so this will be 3p squared. All right, and from here we can simplify. We still have this 3 on the outside in this first binomial that we're multiplying by. But 2n squared is the same thing as 4n squared. And then 2n times 3p will give us a minus 6np. And then finally, 3p squared will give us a 9p squared. So that would be the fully factored form of this polynomial here. Now for section 5.3 here, I do recommend trying to memorize these special types of factoring here. It's going to make your life a little bit easier when you look at these polynomials that you want to factor and be able to recognize if they resemble any of these forms here. All right, so this brings us to section 5.5, and in this section, we're going to solve quadratic equations using what's called the zero factor property. Now, I've written down this property here, and you can also find it in your textbook, but what it says that is that if we are multiplying two things, A and B, and their product is equal to 0, then either A must be equal to 0, or B must be equal to 0, or both could be equal to 0. So we're going to use this property here to solve the following equations. So let's start with question 9 here. We are taking the product of these two binomials, and we say that their product is equal to 0. So in this case, we can think of this as A and this as B, thinking in terms of our zero factor property. So our property says that if that product is equal to 0, then A must be equal to 0, so 3k plus 8 must be equal to 0, or B must be equal to 0, so 2k minus 5. So from here, what we want to do is we want to figure out for which value of k will make this 0, and which value for k will make this 0. So in other words, we need to solve both of these equations for our variable k. So on the left-hand side here, we have 3k plus 8 is equal to 0, so subtracting 8 on both sides will give us this. And finally, we can divide by 3 to get k completely alone, so we get k is going to be equal to minus 8 over 3. So this means for this value of k, plugging this into this equation would make this statement true. Now doing the same thing for this equation here, we'll first add 5 to both sides. So we're going to get 2k is equal to 5, and then we'll divide by 2 to get k completely alone. And so we get k is equal to 5 over 2. So this means this value of k will make this guy equal to 0. So we can conclude that our solution set in this case is going to be minus 8 thirds and then 5 over 2. And so that is our final answer for this question here. All right, so we want to do the same thing for this question here. We want to solve this, and we're going to use our zero factor property. But first, notice we're not taking the product of any two things. So at first, it might not be obvious how we're going to use our zero factor property. However, what we can do is factor this polynomial so that we end up with the product of two binomial terms. So we know we can factor this. The first term, the coefficient of our first term here is just 1, so we know we're going to end up with a factored form that looks like this here, where our first two terms in our binomials are just x. Now, these numbers here, what they need to do is they need to multiply to give us positive 80 and add to give us minus 18. So those two numbers would be minus 10 and minus 8. So when we factor this guy here, we end up with the product of these two binomials, and we know that this whole thing needs to be equal to 0. So from here, we can apply our zero factor property. Doing so, this would be considered A, and this would be considered B here. So our zero factor property says that if this is equal to 0, then either both of these either A needs to be equal to 0, or B, or both of them. So x minus 10 is going to be equal to 0, or x minus 8 is going to be equal to 0, or both. So for both of these, we're going to solve for x. We're going to get that x is equal to 10, or x is going to be equal to 8. So that would be our solution set here. It's going to consist of 8 and 10, and so that's going to be our final answer when we solve this equation. All right, so let's look at this next example here. We still want to use our zero factor property, but again, we don't have the product of anything here. So what we're going to have to do is rewrite this and factor this guy, just like we did in the last example. So first of all, notice that both of these terms share a common factor of minus 3. So what we're going to do is pull that out from both terms here, and we're going to be left with x squared minus 9. And this is going to be equal to 0. Well, we know from our last section that this is going to be the difference of squares. We have x squared minus 9, and 9 can be rewritten as 3 squared. And we know that to factor the difference of squares like this, we're going to get x plus 3 and then times x minus 3. And so this whole thing is going to be equal to 0. Now, notice we have the product of two binomials here, so we can use our zero factor property. This will be a, and then our second binomial here can be thought of as b. Now, we don't have to worry about this minus 3 on the outside, because if this is 0 or this is 0 or both, no matter what, this is still going to be equal to 0. This minus 3 is not going to affect this, since this is the product of these three terms here. So as long as one or both of these is 0, this statement will be true here. So we're just going to focus on our a and b's. This means x plus 3 is going to be equal to 0, or x minus 3 is going to be equal to 0. Now, clearly, solving for x, we're going to get minus 3, and x is equal to positive 3. So in this case, our solution set is going to consist of the x values when x is equal to minus 3 and positive 3. Now for this next example here, notice that we do have the product of two binomials, so we might want to use our zero factor property right away. But the thing is that this does not equal to 0. So we're not able to use that property yet. What we first have to do is rewrite this equation. So we can do that by using our distributive properties and combining like terms. So what we're going to do is FOIL this here, so that on the right hand or the left hand side of this equation here, we're going to end up with x squared plus 6x minus 16, and this is all going to be equal to minus 21. So from here, what we're going to do then is we'll add 21 to both sides of this equation here, so that we do end up with 0 on the right hand side. So doing that, we're going to add 21 to both sides here. We're going to get x squared plus 6x plus 5 on our left-hand side, and this whole thing is going to be equal to 0. Now, from here, what we can do is factor this polynomial so that we end up with the product of two binomials. Now, since the coefficient of our squared term is 1, we know that this is going to look like the product of two binomials whose first term is going to be x. So it'll look like this here. Now, these numbers here need to multiply to give us 5 and then add to give us 6. And so those numbers are going to be plus 5 and plus 1. Now, from here, we can use our zero product or our zero factor property now, because we have the product of these two binomials. So this will be our a and this will be our b. So we'll have that x plus 5 is going to be equal to 0, or x plus 1 is going to be equal to 0. Now solving for x, this tells us that x is going to be equal to minus 5, or x is going to be equal to minus 1. So our solution set is going to consist of negative 1 and negative 5. So these values of x will make our original equation here true. Now for this next example, we're again going to have to rewrite this equation here so that we can get it into the form that we want to use our zero factor property. So the first thing that we want is we want the right-hand side to be 0. So what we can do is we can subtract off 3x on both sides. So that we're going to end up with x cubed minus 2x squared minus 3x. This is going to be equal to 0. So now from here, what we're going to want to do is factor this so that we do end up with the product of two binomials here on our left-hand side, and then we can apply the zero factor property. But notice that we have x cubed, x squared, and x here. So all of these terms share a common factor of x. So what we can do is pull that guy out, and the resulting polynomial on the inside is going to be easier to factor. So now, since the coefficient of this guy here is 1, we know that the resulting binomial is going to be of this form here. And then the two numbers that go here need to multiply to give us negative 3 and then add to give us negative 2. So those numbers are going to be negative 3 and positive 1. Now, notice that we end up with the product of three terms here. So in this case, our zero factor property can be applied to these three terms. X could be equal to 0, or x minus 3, or x plus 1 could be equal to 0, or all three of these could be equal to 0. So we're going to end up with three solutions in this case. The first one is x being 0. If we plugged 0 into this x here, we would get 0 times this, which is in fact equal to 0. Or x minus 3 could be equal to 0, or x plus 1 could be equal to 0. So what we're going to do is solve for x in both of these equations here, and we end up with three solutions. So our solution set in this case is going to consist of x values, -1, 0, and 3. Now for this next example here, we're going to use a quadratic equation in an application. So we're told that there's a sign that has the shape of a triangle. The length of the base is 3 meters less than the height. And what we want to do is figure out the measures of the base and height given the area of the triangle. So for these particular problems, it's always a good idea to draw a sketch so you have a good idea of what's going on. So we have a triangle, and we'll call h the height of this triangle. And we're told that the base of this triangle is 3 meters less than the height. So that means we'll call our base b. The base is going to be the height of this triangle minus 3 meters. Now, we're given the area of this triangle. It's going to be 44 meters squared, and we know that the area of the triangle is going to be half times base times height. So that means the area of this triangle, since it is 44 meters squared, we have an equation here. We have 44 is going to be equal to half times base times height of this triangular shaped sign. Now notice though that we can rewrite the base of this guy in terms of our height, meaning this equation can then become 1/2 times base, which is h minus 3, times our height. So what we want to do in this case is distribute and simplify the right-hand side of this equation. So the first thing that I'm actually going to do is distribute this h to both terms inside of our parentheses here. We're going to get 1/2 times h squared minus 3h on the right-hand side. Now the next thing we could do, we could distribute this 2 to both terms here, but then we're going to end up with fractional coefficients for both of these terms. What we can do instead is multiply both sides of our equation by 2 to cancel out this fraction. Doing so, we're going to end up with 88 on our left-hand side, and that'll be equal to h squared minus 3h. Now notice this is starting to look familiar. This is starting to look like the quadratic equations we've been dealing with. And in fact, if we subtract 88 on both sides of this equation here, we're going to end up with h squared minus 3h is minus 88 is equal to 0. So now we have this quadratic equation here, and then remember the question asks us to find the measures of the base and the height given this area. So using this equation, what we can do is solve for h. We can find the height of this triangle, and then using that value, we can plug that into this equation to find the base. So what we can do in this case is factor this guy and use our zero factor property. We know that the fully factored form of this guy is going to be of this form here. And then the two numbers in this case need to multiply to give us minus 88 and add to give us minus 3h. So those two numbers are going to be minus 11 and plus 8. I'm going to have 8 here. There we go. Now, our zero factor property says that this is going to be equal to 0, or this is going to be equal to 0, or both. So this tells us that our height could be 11, or our height could be -8. But notice with these application problems, these are real world problems, and it wouldn't make sense for the height of something to be a negative. So this would not be part of our solution set because we can't have negative height. All right, so our only solution then for our height in this case would be 11 meters. But remember, we also want to find the base of this triangle. So if we have that the height is 11, we can plug that into our equation for our base. And so we're going to end up with 8 meters. So the height of this triangular sign is going to be 11 meters and the base is going to be 8 meters. All right, so for the last question in this section, we want to solve this equation here for our variable r. So as we can see, we have r terms on both the left and right hand sides of our equation, so it'd be a good idea to kind of get them on the same side of our equation. So that'll be our first step here. So what I'll do is I'll subtract r on both sides. I'm going to be left with 2k plus ar minus r is going to be equal to negative 3y. Now, what I can do is I can bring this 2k onto the other side of our equation here, so we just have our r terms by themselves on the left-hand side. Doing that, so subtracting 2k on both sides, I'm left with ar minus r on the left-hand side, and then minus 3y minus 2k on the right-hand side of our equation. Now notice, both of our terms here on the left-hand side share a common factor of r. So what we can do is pull that common factor out, and we're left with this on the left-hand side of our equation. And then we still have this on the right-hand side. Now remember, what we want to do is solve the equation for r. So we want to get r completely by itself. So we can do that by dividing by this a minus 1 on both sides. Then we're left with r by itself, and then we have minus 3y minus 2k all over this a minus 1. So this would be our final answer here. We solved this equation for r. All right, so this brings us to section 6.1 here, and we're going to start with this question. We want to give the domain of this rational expression using both set builder and interval notation. But before we start, just a quick reminder of what a rational function is. It's a function that's defined by a quotient of polynomials. So that's what this looks like here in the right-hand corner. This would be a rational function. And so as we can see, we have a quotient of polynomials here, but this is only going to be defined when our denominator here is not equal to 0. Remember, we can never divide by 0. So that means this function here is not going to be defined for any values that'll make this function in the denominator equal to 0. So all of those values are not going to be within our domain of our rational function. Those values would put a restriction on our domain. So going back to this question here, if we want to give the domain of this guy, we know that this function is going to take as an input all real numbers except those which make this denominator here 0, because that would make this entire function undefined. So what we need to do is figure out which values for x will make this denominator equal to 0. And we can do that by setting up an equation here. Our denominator is 2x minus or plus 7. We want to figure out when this is equal to 0, and we can do that just by solving for x here. Now solving for x, this will give us minus 7 over 2. So if we were to plug this x value in to our denominator here, minus 7 over 2, we would end up with 0 in our denominator. So this means this guy cannot be part of our domain. So to express our domain in set builder notation, we're using set notation here, so we're going to start with our brackets, and we're saying all x values such that, so that line there represents such that, our x values are not going to be equal to minus 7 over 2. So that's how we would express our domain for this problem in set builder notation. And then in interval notation, we're a little more familiar with this here. We're going to say all real numbers except minus 7 over 2. So this will be from negative infinity up to minus 7 over 2, but not including it. And then union minus 7 over 2, not including that guy, all the way up to positive infinity. All right, so for these next several examples here, what we want to do is write each rational expression in its lowest terms. So essentially, we are going to simplify each of these guys, and we can do so by factoring each of these rational expressions and then seeing what can cancel with our numerator and denominator here. So for this first example, notice that we have a difference of squares. We have t squared minus 3 squared, which is 9. So the top of this rational expression here, this numerator, can be factored to t plus 3 times t minus 3. All right, and then notice in the denominator, we have 3t plus 9, so both of these terms share a factor of 3. So if we were to pull that common factor out, we'd be left with t plus 3 in the bottom. Now notice since we have a t plus 3 in the top and bottom, these guys are going to cancel, and then we're left with t minus 3 on the top over 3. And so this would be this original rational expression in its lowest terms. All right, so let's do the same thing for question 45 here. Again, the first thing that we want to do is see if we can factor each of these polynomial expressions. So in the numerator here, we see that the coefficient of our squared term is 1. So we know that the factored version of this is going to have this form here. And we just need to figure out what's going to go in these spaces. Now in these spaces, these numbers need to multiply to give us minus 15 and add to give us positive 2. So those two numbers are going to be negative 3 and positive 5. Now we have the numerator factored. We want to do the same thing in the denominator. We again know that the factored form is going to look like this here. And our two numbers need to multiply to give us 5 and add to give us 6. So that'll be these numbers here. Now notice we have an x plus 5 in the numerator and the denominator, so those guys will cancel. Then we're left with x minus 3 over x plus 1, and we can't simplify any further, so this would be our rational expression in its lowest terms. Now this next question here is a bit of a special case, and that's because notice in the numerator we have a positive 7 and a minus b, but in the denominator we have a positive b and a minus 7. So our numerator and denominator are opposites. So what we can do in this case is we can factor one of them and rewrite it so that they're no longer opposites. So what I mean is, if we were to keep the numerator as is, but factor out a minus from our denominator, so bringing out a minus, that would change the signs of both of these terms here. So we would end up with a minus b and a plus 7. Now rewriting this, we still have this 7 minus b on top. We have this minus 1 on the bottom, and this in parentheses, so becomes 7 minus b. So now notice we have a 7 minus b on the top and bottom here. So these guys can cancel. Then we're just left with 1 in our numerator and negative 1 in our denominator, which fully simplifies to give us a minus 1. Now, even when we're multiplying or dividing these rational expressions, it's always a good idea to factor these guys and see what can cancel. So for this first example here, we want to multiply these two rational expressions. So we know when we're multiplying fractions, we can just multiply straight across. So this will be 4x times 14x plus 7, and then 8x plus 4 times 6. Now what we could do here is we could distribute this 4x to both terms here and this 6 to both terms here, and then try to combine and simplify. But like I said, it's going to make our lives a little bit easier if we first try to factor these guys. So notice, if I leave this 4x out here, both terms in my parentheses here share a common factor of 7. So if I were to pull that out, I'd be left with 2x plus 1. And then in the denominator here, the two terms in the parentheses here share a common factor of 4. So let's pull that out also. We're going to be left with 2x plus 1 times 6. So doing this, we're left with 2x plus 1 in the numerator and the denominator, so those guys are going to cancel. Notice that we also have a 4 and a 4 in our numerator and denominator, so those cancel as well. And so we're left with x times 7 in our numerator, so that'll just be 7x. And then in our denominator, we're just left with 6. So this would be our final answer here. Now, something to note here, we could have just distributed these guys and combined like terms and simplified, and you'd end up with the same answer. But doing it this way, where we factor first and try to cancel these common terms, makes our lives a little bit easier when trying to multiply or divide these rational expressions. Now, something else to note here is that we were able to cancel these 4's here because in the top and bottom, the 4's are multiplying everything here and then everything here. So in the top, this is all considered one term, and in the bottom, this is considered one term. If we had multiple terms here, so for example, if we had 4 plus something and then 4 plus something, we wouldn't be able to cancel those 4's because they wouldn't be connected through multiplication. The addition or subtraction would separate those terms. So also something to keep in mind there, we're only able to cancel these guys because they're multiplying everything in our numerator and then everything in our denominator. All right, so this brings us to our last question in this section. In this case, we want to divide these two rational expressions. Now, before we go ahead and do that, the first thing we're going to want to do is factor both of these guys to see if we can simplify and cancel anything. So notice for this first expression here, both terms in our numerator share a common factor of 4. So we can pull that out, and then we're left with x minus 5 in our numerator. And then we still have this 5x in our denominator. Now for our second expression here, again our numerators share, or both terms in our numerator share a factor of 2 in this case. So we can pull that guy out, and we're left with this here. So now this becomes our new problem. What we want to do is divide these two rational expressions. Now remember, when we are dividing fractions, it's the same thing as multiplying them by the reciprocal. So if we want to divide our first fraction by this one, what we're going to do is multiply this first fraction by the reciprocal of this one. So the reciprocal of this would be this here. And so now this becomes our new problem. Now, remember when we multiply fractions, what we're going to do is just multiply straight across. So we're going to have 4 times x minus 5 times this, and 5x times this. So doing that, we're going to have x minus 5 in our numerator and our denominator. So these guys are going to cancel right away. Then what we're left with, we're going to have 4 times 7x cubed over 5x times 2. So this becomes much easier to do. We're going to end up with 28x cubed divided by 10x, and then we can simplify this. We have an x in our numerator and denominator, so those will cancel. Then 28 and 10 also both share a factor of 2. So we can divide both of these guys by 2 here. What we're going to be left with, we have 28 divided by 2, which will give us 14, and then we still have x squared in our numerator. Now in our denominator here, we're just going to end up with 5. Alright, so this brings us to section 6.2, and in this section what we're going to be doing is adding and subtracting rational expressions. So the key here, just like when we are adding or subtracting fractions, is to make sure that we have a common denominator in order to do so. So let's look at this example here. We want to subtract these two guys. Now, we don't have a common denominator, so we're going to have to multiply one or both of these fractions to get a common denominator. Now notice this one we have 18a cubed b squared, and here we have 9ab. So what we can do is just multiply the second expression here by 2a squared b. Doing so, we're going to multiply the 9 and 2, that'll give us 18, and then a and a squared will give us a cubed, and b gives us b squared. So that's what we'll multiply this guy by, and whatever we do to the top, we have to do to the bottom. So this becomes, we have our original rational expression here, and we're subtracting out this new expression. 2 times 2a squared b is going to give us 4a squared b, and on the bottom, we're going to have our common denominator here. So now that we have our common denominators, all we have to do is subtract our numerators. So we're going to have 7 minus 4a squared b over our denominator here. And we can't simplify this further, so this would be our final answer. Now for this example here, we're adding these two rational expressions. Now in order to do so, we again need to get a common denominator. And to do that, what we're going to have to do is multiply each of these rational expressions by the denominator from the other expression. So what I mean is we can rewrite this sum here. We have our first expression. What we're going to do is multiply the top and bottom of this expression by the other denominator. And then we're going to do the same thing with our second expression here. We're going to multiply the top and bottom by the denominator from our first expression. So this is our new problem here. What we're going to do is multiply these guys out and simplify before we can add them together. So for our first expression here, we're going to have 2x times x minus 7. And then our denominator is going to become x plus 4 times x minus 7. Now for our second expression, we're going to get 3x times x plus 4. And then we have a common denominator, this here. So like I said, first we are going to try to simplify these expressions. What we can do is we can multiply this 2x to both terms here and this 3x to both terms here. Doing so, we're going to get, we'll have 2x squared minus 14 x. And then since we now have a common denominator, we can add these guys across. So we're just going to add straight across our numerators. So this is our first numerator here. It turns into this when we distribute the 2x. And our second one is going to turn into 3x squared plus 12x when we distribute that 3x to both terms. Now, since we have our common denominator, this will just all be over x plus 4 times x minus 7. Now from here, we can combine like terms. We have 2x squared, a 3x squared, and then a minus 14x and a plus 12x. So combining these like terms here, we're going to get a 5x squared and then minus 2x in our numerator. And this is still all over our common denominator here. Now what we can do, the last step to fully simplify this is notice in our numerator, both of these terms share a common factor of x. So the fully simplified form here would look like this. And so this would be our final answer when we subtract the two rational expressions here. Now for this next example here, we're adding three rational expressions, but the idea remains the same. We first need to get a common denominator before we add them together. So notice the denominator in this first expression is in a sense bigger than the other two. So we want to try to see if we can multiply these two rational expressions by something to get a common denominator of this here. So we have our first rational expression here. And let's try to multiply our second and third expression by something that'll give us this common denominator of y squared plus 3y. Well, for the second term here, if I were to multiply the top and bottom by y plus 3, that would give me exactly y squared plus 3y. Similarly, for our third expression here, if I were to multiply the top and bottom by y, that would give me exactly y squared plus 3y. So, performing these multiplications here, we still have this first expression. And our second expression is going to become 2 times y plus 3 over y squared plus 3y. And our second is going to become 5y over y squared plus 3y. So as you can see, we have our common denominators, so we can add these guys together. We're still going to have 15, so what we're going to do is add these three numerators together. Now notice our second numerator here, if we distribute this 2, this will become 2y plus 6. So we're going to write that here. And then we still have this plus 5y. And this is all going to be over our common denominator of y squared plus 3y. Now from here we can combine like terms. We have 2y plus 5y and then 15 plus 6. So combining our like terms here, we're going to end up with 7y plus 21 over our common denominator. But something to note here, we can simplify this further. Notice our terms in our numerator both share a common factor of 7. So we can factor that guy out and we're left with y plus 3 in our numerator. Similarly, in our denominator, notice both of these terms share a factor of y. So if we were to factor that guy out, we'd be left with y times y plus 3. And then as you can see, we have a y plus 3 in our numerator and denominator, so those guys will cancel. And so our final answer here is just going to be 7 over y. Alright, so for the last question in this section here, we're adding these two rational expressions, and in the denominator of both of these guys, we have these polynomials. Now, we might want to multiply the top and bottom of each of these expressions by the denominator and the other guy, but that's going to get very messy very quickly. Instead, what we can do is we can see if we can factor both of these polynomials here and see if they have any factors in common. So, what we're going to do is rewrite this. Factoring our first denominator here, since the coefficient of our squared term is 1, we know our factored form is going to look like this here. Now, the numbers here are going to be -2 and -2 since they multiply to give us +4 and add to give us -4. Now, doing something similar for this next expression here, factoring our denominator, we're going to get m plus 3 times m minus 2. So notice that the factored form of both of these polynomials here share a common factor of n minus 2. So that means if we want to get a common denominator, for this one, all we need to do is multiply the numerator and denominator by n plus 3. And for our second expression, we just need to multiply the numerator and denominator by m minus 2, since we need to have two m minus 2 factors like this one here. So doing that, we're going to end up with, we'll have 2 times m plus 3 in the numerator, and then in our denominator here, I'm going to write m minus 2 squared, since we have an m minus 2 times an m minus 2, so just writing this in a more compact form, and this is times m plus 3. Now for our second expression here, we're going to have 3 times m minus 2 over, so now we have m minus 2 times m minus 2, so that'll give us m minus 2 squared, and this is being multiplied by m plus 3. So doing that, multiplying each of these expressions in the numerator and denominator by the missing factor in these factored polynomials gives us a common denominator. So from here, we'll distribute this 2 to both terms, in our parentheses here. So we're going to have 2m plus 6, and since we have a common denominator here, we're going to write all of this over one common denominator. So our second numerator here, we're going to distribute this 3 to both terms there, so we're going to get 3m minus 6. Like I said, this is going to be all over our common denominator here. Now from here, we can combine like terms and simplify. Notice that we have a plus 6 and a minus 6, so those guys are going to cancel, and then we have a 3m and a 2m. So adding those guys together, we're going to get 5m, and this is all going to be over our common denominator. So we can't simplify further, so this is going to be our final answer here.